Hi, I'm Kai, an undergraduate student at National Yangming University. Our co-authors, Liu Ling, Shuai Honghan, and Zheng Honghuang are also come from National Yangming University. The paper I will be presenting today is titled Mimicking the Annotation Process for Recognizing the Microexpressions. So first, I want to introduce what are microexpressions. Microexpressions just like the normal expressions. However, they always last only a few seconds. And also, it is hard for our human eyes to recognize the microexpressions. And here's an example. Here is a sequence of a microexpression. And it is hard for our human eyes to distinguish the differences between each of them. So, microexpression recognition is to recognize the microexpressions. And there are two common ways to recognize the microexpressions, either from sequence of images or using amplified image. An amplified image is obtained from sequence of images. And this amplified frame is easy for human eyes to recognize the expression. For example, you can just easily recognize this girl has negative emotion. And after we have this sequence of images, we can obtain the labels after we try to recognize it. So for the first one, it has the happiness label. And for the second one, it has the repression label. And our motivation is to mimicking the annotation process. And why we want to mimic the annotation process? Because if we can annotate the annotation process, we can obtain more accurate results. And here's the process for how the data sets annotate their data. So here we have a lot of images, and here I only show one image here, for example. And the images will be encoded by facial action coding system to obtain a lot of different AU labels. For example, this image can be encoded into AU12. And what is AU represent? AU represents the action unit, which describes the movement of the facial muscles. And after obtaining tons of thousands of images and AU labels, we can build a connection between AUs and expressions. For example, next time we see AU12, we can link it to happiness, or we see another AU, we can link it to another expression. And one important property is that AU either describe eyes or mouth area, but not both. So it provides us an idea to separate eyes and mouth area because they have different AU labels. And here comes our methods, and we just separate this part into 3 small sections. First, there are 2 common ways to do the preprocessing, either from motion magnification or from optical flow. However, using motion magnification reveals little or no information about the changed area. Additionally, optical flow provides no clear pattern about the changed area. So to solve these 2 issues, we're trying to combine these 2 methods to obtain a new input. Here is an example. We can first amplify the frame of onset and apex frame to obtain amplified image. And next, we can compute the optical flow frame from amplified frame and apex frame. And also, we can obtain another optical flow frame from amplified frame with offset frame. And these 3 new images can be formed as a new input. The next step is to separate the facial areas. So we will make our image into 2 small parts, that is eyes part and the mouth part. One reason for the facial separation is mentioned before, that AU labels are independent between eyes and mouth. Another reason is that eyes and mouth have different features. So using facial separation, we can extract different features from different facial regions. The next step we want to do is to increase the training diversity. So we introduce a new data augmentation technique called region replacing, and we abbreviate region replacing into RR. And what it does is it will randomly replace the same class subject facial area. Here's an example. Here are 2 samples, and they are both happiness in the same class. And maybe they can exchange the eyes image or the mouth image if they select each other. Because maybe when the first one are replaced by another one, that doesn't mean this one should be replaced by this one. But here we just show exchanging here for easy understanding. So what region replacing does is to exchange maybe their mouth area from this animation. And one advantage that using region replacing is that it can eliminate the bias between the samples. Next, after talking about data preprocessing, we will move on to dual branch architecture. And after obtaining the facial regions images, we will send these facial region images into the same base layer, followed by two different layers. And these two different layers are used to extract different region features. And our layers are designed based on ResNet 18 with shuffle attention. Table here shows the details about the layers. However, directly using the region features is not enough because different facial regions should have different weights. So we introduce area-weighted module to compute the weight for different facial regions. So after obtaining area-weighted module, which is abbreviated into AWM, we will make the model know which kind of features is more important than the others. And here is the detail about the area-weighted module. The unweighted features from different regions from eyes and mouth will first be concatenated to form a new input. And these features will be sent into two fully connected layers and followed by a sigmoid activation function to obtain feature weight. And this feature weight is used to represent the importance of each entry. To further improve our model performance, we incorporate AU label into training. However, directly using AU label can come across a severe data imbalance issue. So we decide to use similarity score to train our model. And using supervised contractive loss is our choice because it is one of the most powerful methods to train the similarity score task. However, using supervised contractive loss will face a severe multi-AU label issue. For example, for AU4 and 7, it will consider both AU4 and AU5 as negative sample. What we want is that AU4 and 7 has higher similarity score compared with AU5. So what we do is to introduce a weight into the loss, and we call this new loss weighted supervised contractive loss. And our loss is computed on the weighted features from different samples. For the upper one is one sample, and the lower one is another sample. And here's the details about our loss function. First, we will compute the weight from the ratio of intersection and union of AU labels. After we have the weight, we will inject the weight into a loss. So the original loss, there's no W here. So we just inject W here to tell that the similarity about different AU labels. And this provides more flexibility to train the similarity score. And we also show the notation on the bottom left of our slide. So here's the overall architecture. Let me summary again. First, we will do a preprocessing from the original image. And next, we will send the preprocessing image into the dual branch architecture. And the dual branch architecture will use to train the model and obtain the final results. And here we use area-weighted module to compute the weights for different facial region. And we also use AU alignments to align the AU features. To show that our model design is helpful and can surpass other methods, we design different experiments. So the first one we want to show is the performance of our model. And we test our model performance on CASME2 and SAM, which are two common benchmark datasets for examining the microexpression recognizer. And the details about each number of classes is shown in this table. Because the previous methods all used two different kinds of comparison, that is 5 categories and 3 categories. So we follow their settings into our training, and we just show the result in the next page. So here's the metrics we used. We used 3 different metrics: accuracy, unweighted F1 score, and unweighted average recall. And the details about each loss here is shown in the notation on our left bottom. And TP represents true positive, and FP represents false positive, and S here represents the subjects. So we will compute each matrix on each subject first, and finally we will just obtain accuracy for the average of each subject. And Fn represents false negative, and Ni represents the number of samples within class I. And C represents the number of classes. For example, we have 5, we have 3. And here's the 5 categories comparison. And we can easily observe that our model can outperform other existing methods on both accuracy and unweighted F1 score. And here's the improvement of our model accuracy and F1 score. And why our model can outperform this existing methods, because our model can handle those small number of samples. It can perform. It has higher accuracy and F1 score on those samples. For example, here in maybe like surprise, it only have 25 samples and 64 in discuss. However, our model can also perform well to classify surprise, and this is why we can obtain higher performance. And the next thing is the 3 categories comparison, and we also surpass other existing methods. And here's our model improvements. And why we can obtain a highest improvement is because that 3 categories comparison has few classes, so it is more easy task for our model to do. To test our model components, we design different experiments, and here the tables just show the summary of our findings. And SB represents single branch, AU represents AU alignment, DB represents dual branch, and AWR represents area weight module. R is used to represent region replacing. And we can easily observe that using all the components and methods, we have the highest performance. So here's our findings. In terms of region replacing, it is helpful to training, and it provides more information to SAM, and we will explain this phenomenon later. And next, AU alignment and AWM both are useful to training. However, using AU alignment can lower the performance of single branch model. And our possible explanation is that using single branch model is not enough to extract the right region features, because what we want to do in AU alignment is to align the AU features, and AU features is related to our facial region. So single branch model is not enough to extract the correct facial features. The final one is dual branch vs single branch model. And without AWM and AU alignment, the single branch model can win. And this also shows that using AWM and AU alignment is helpful to train our model. And adding only AU alignment to dual branch model, the dual branch model can win. And our speculation is that using AU alignment is enough to provide the facial information to our training. So our model can just find out the right features, and it can finally classify the labels correctly. To show that our model can really capture the AU features, we just plot the features distribution. And the left one is for the Casimir-2, and the right one is for the SAM. And from these 2 distribution plot, we can easily observe that our model can cluster the similar labels into same cluster. So here the legends represent the AU labels. The plus sign just used to connect multi-AU labels. So the similar color represents similar AU labels. And here is some interesting findings. Casimir-2 has more AU categories. However, SAM has more internal differences between AU labels. So this is why using region replacing provides more information to training, because using region replacing, we can bring more internal information about the AU labels to our model, because we just exchange the facial features, and facial features, the facial image can reveal more, it's related to AU label. So this is why SAM can benefit more than Casimir-2 from region replacing. The final part of our experiment is AUCAM. And why we want to design AUCAM is to observe the relations between AU features and facial regions. And what we don't want to observe is how the model made the decision, because we want to prove that our model can really extract the right AU features from the right facial region. So this is why we use AUCAM. So here's a comparison about these two methods. And here is our equation to obtain the AUCAM. We will first obtain the AUCAM for both eyes and mouth. So B is eyes or mouth. And other big A and small a is represent the weight, and big A is the output from our module. And after we obtain each facial cam image, we will concatenate together to form AUCAM. So here we designed 3 different scenarios to examine that AUCAM has better visualization for AU features and facial regions. The first scenario, we just choose AU12 with different subjects and the same clauses, at the same clause. And we can easily observe that using AUCAM, our model can extract the similar facial region and has similar interest regions. However, GradCam provides little internal information. The next one, we just pick up the same AU15 with the same subject but with different classes. Because we have the same AU label, so AUCAM should capture similar interest region, and it just successfully capture out the similar regions. However, GradCam just only show the eyes image and didn't provide more internal information than AUCAM. The last one, we just pick up AU14 with different classes and different subjects. Because we have same AU label again, so our AUCAM can successfully capture out the similar region information. Compared with GradCam, it didn't provide a lot of it didn't share a lot of internal information. So using AUCAM really help us to observe how our model link the AU feature to facial regions. To sum up, we propose dual branch model which separate different facial areas, and this is inspired from how some dataset annotate. And we also show that using AUCAM, we can observe the AU relations, and this can also be used in other tasks such as maybe facial expression recognition, or even in AU classification. And our future work will focus on how to extend our models, and we can add graph neural network into our structure to reduce the noise and provide more node information. And this is all about our presentation. Thank you.